Welcome back to Operating Systems Crashcast. I'm Victor, and today we're diving into a crucial topic in process synchronization, the critical section problem. Sheila, are you ready to unravel this mystery?
Absolutely, Victor. This is a fundamental concept in operating systems and concurrent programming. It's something that every developer and system designer needs to understand.
You're right, Sheila. Let's start with the basics. Can you give our listeners a clear definition of what a critical section is?
Certainly, Victor. A critical section is a segment of code where a process or thread accesses shared resources, such as variables, data structures, or devices. The key point is that these resources can be accessed by multiple processes, but we need to ensure that only one process can execute its critical section at any given time.
That's a great explanation. It's like a single-lane bridge that can only accommodate one car at a time, right?
That's an excellent analogy, Victor. Just like cars need to take turns crossing a single-lane bridge to avoid collisions, processes need to take turns executing their critical sections to avoid conflicts.
Now, this brings us to an important concept related to critical sections: race conditions. Can you elaborate on what these are and why they're problematic?
Of course. A race condition occurs when multiple processes or threads try to access and manipulate shared data simultaneously. The outcome of the program becomes dependent on the timing or order of execution of these processes. This can lead to unpredictable results and bugs that are often hard to reproduce and debug.
That sounds like a recipe for disaster in software development. How do we prevent these race conditions?
That's where the concept of mutual exclusion comes in. Mutual exclusion ensures that if one process is executing in its critical section, no other process is allowed to execute in its critical section. This is the primary goal when solving the critical section problem.
I see. So, we need some sort of mechanism to coordinate access to these shared resources. Are there specific requirements for a good solution to the critical section problem?
Absolutely, Victor. There are three main requirements that any solution to the critical section problem must satisfy. 1. Mutual exclusion. As we mentioned earlier, only one process can be executing in its critical section at any given time. 2. Progress. If no process is executing in its critical section and some processes wish to enter their critical section, only those processes not executing in their remainder section can participate in deciding which will enter its critical section next. This decision cannot be postponed indefinitely. 3. Bounded waiting. There must be a bound on the number of times that other processes are allowed to enter their critical sections after a process has made a request to enter its critical section and before that request is granted.
Those are some stringent requirements. It seems like a delicate balance between ensuring fairness and maintaining system efficiency. Can you give our listeners an idea of why this problem is so important in modern computing?
Certainly, Victor. The critical section problem is at the heart of concurrent programming and parallel processing. In today's world, where we have multi-core processors and distributed systems, efficient solutions to this problem are crucial for 1. Ensuring data integrity in databases and file systems. 2. Coordinating access to shared hardware resources. 3. Managing concurrent transactions in e-commerce systems. 4. Synchronizing threads in multi-threaded applications. 5. Preventing deadlocks and live locks in operating systems.
That really puts it into perspective, Sheila. It's clear that understanding and solving the critical section problem is essential for building reliable and efficient software systems. Are there any common pitfalls or misunderstandings that developers should be aware of?
Great question, Victor. One common misunderstanding is thinking that simply using atomic operations or hardware-level synchronization primitives will solve all concurrency issues. While these are important tools, they're not a silver bullet. Developers need to carefully design their concurrent systems, considering factors like 1. Granularity of locking. 2. Potential for deadlocks. 3. Performance implications of excessive synchronization. 4. Ensuring fairness in resource allocation. It's also worth noting that different programming languages and platforms may provide different mechanisms for handling critical sections, so it's important to understand the specific tools and best practices for your chosen environment.
Thank you, Sheila. That's a wealth of information about the critical section problem. To wrap up, could you give us a quick recap of the key points we've covered today?
Certainly, Victor. Here's a summary of what we've discussed. 1. A critical section is a part of a program where shared resources are accessed. 2. Race conditions occur when multiple processes compete for shared resources. 3. Mutual exclusion is crucial to prevent race conditions. 4. Any solution to the critical section problem must satisfy mutual exclusion, progress, and bounded weighting requirements. 5. The critical section problem is fundamental to concurrent programming and modern computing. 6. Developers need to be aware of potential pitfalls and consider various factors when designing concurrent systems.
Excellent summary, Sheila. That brings us to the end of today's episode on the critical section problem. Thanks to all our listeners for tuning in. Remember, understanding these concepts is crucial for anyone working with operating systems or concurrent programming. Until next time, keep exploring the fascinating world of operating systems.